Welcome to this video about the impact of climate change and climate change policy in the United States. What we are going to cover in this video is first the physical aspects of climate change, in the sense that we are going to look at the increase in temperature. Then we are going to talk about climate modeling, and this leads us directly into future climate trajectories. Note that the climate modeling aspects are necessary to understand in order to better grasp what the future climate trajectories are based on. Then, once we have those future climate trajectories, we are going to look at the impact of a changing climate on economic activity in general, but then we also look at a particular example of how climate change is impacting agricultural production. The second part of this video is going to be talking about climate change policy. When we are talking about climate change policy, then usually we talk about mitigating climate change and also about the adaptation of climate change once it happens. Specifically, we are going to look at a carbon tax, and we are also going to look at how initiatives to decarbonize the transportation sector have wide-ranging implications. Now, we are going to focus here on energy and environmental policies and how they impact agriculture and transportation. And it should be kept in mind that this is a very broad topic and there is much more to cover. So this video is only going to give you a very short glimpse at some aspects about climate change and climate change policy in the United States. And you will see that throughout the video, I'm going to present sources or resources, reports that go into much more detail. Now, before we start, let us first have a look at this newspaper article that is actually from a newspaper in New Zealand. And the newspaper article reads that the furnaces of the world are burning about 2 billion tons of coal a year. While this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. This tends to make the air a more effective blanket for the Earth and to raise its temperature. The effect may be considerable in a few centuries. What I like about this article is that it very briefly describes climate change in the sense that we are emitting fossil fuel. The carbon dioxide or the fuel then unites with oxygen, creating carbon dioxide, creating this blanket and increasing the temperature, leading to climate change. Now, what is stunning about this particular article is that it was actually published in 1912. Note that if you think that, as I did when I first read this article, that it is, how can they know in 1912, or that this may be fake news? So it turns out that there is also a link to the National Library of the New Zealand government, where you can actually see the original article. So we have been known for the physical aspects or the mechanics of climate change for a very long time. Now, when I talk about the physical aspects of climate change, usually what is meant by that is that we have the impact of CO2 and other greenhouse gases, like, for example, nitrous oxide or methane, on the Earth's atmosphere, and then how this increase in CO2 emissions then is going to translate into changes in temperature and precipitation. Now, there is very little, to a certain degree, there's very little uncertainty about the physical aspects of climate change. Where there is considerable discussion are the social aspects of climate change, in the sense that knowing that the CO2 that is emitted into the atmosphere, that it causes an increase in temperature that is going to likely change the climate on this planet. What are the mitigation and adaptation measures of societies? How much does it cost? And what should we be implementing? Note that right now a lot of focus has been on avoiding GHG emissions by implementing carbon policies, but that at some point there will also be the switch to adaptation measures, in the sense that we do see climate change happening. We do see the negative effects of climate change, and then the question is, how are we going to adapt to those effects? Of course, there are complex interactions between policy designs, climate change, and human behavior. And I will be getting in some details throughout this video. Again, there are plenty of resources outlining both aspects, the physical aspects as well as the social aspects. At the global level, we have the Intergovernmental Panel on Climate Change, which have multiple what are called assessment reports that happen every 6 or 7 years. The most recent assessment report is the Assessment Report 6, AR6. And when you're going on the webpage of the IPCC, then you can download those articles, and it gives you significant detail about the various aspects surrounding climate change. Usually there are 3 different reports. There are 3 different working groups. One is the physical aspects, in the sense that what happens in the atmosphere when we emit CO2. Then there is about the impacts of climate change on nature and humans. And then there is also the social aspects, or the mitigation and adaptation measures that can be taken. If you're specifically interested in the United States, there's the US Global Change Research Program, and they have the National Climate Assessment Reports. The most recent is from 2018. And you will see that I am drawing a lot of the material, or a lot of the graphs which I show you at the beginning is actually taken from this National Climate Assessment Report, or NCA 2018. Now, let us have a look at some of the climate change indicators, and you see that when it says NCA 2018, that this is the National Climate Assessment Report. So first, we see that we have a change in the annual average temperature in the United States, and soon we are going to look at a particular animation that was done by NASA that shows this change in temperature at the global level. We do have, due to this increase in average temperature, we do have changes in heat waves, as well as heavy precipitation. This translates also into drought conditions. We also see that the Arctic sea ice extent is decreasing. Again, there are many aspects related to climate change. So the effects here would be rises, for example, in sea level. And what we are going to look particularly about on what we are going to analyze in particular in this presentation, when we're talking about agricultural yields, is that we are looking at the heating degree days and cooling degree days. And what this means is, and how those change, and what this means is, I will be showing you in a bit. So again, there are many aspects associated with climate change, and we are only going to cover a very small aspect of those, or very small portion of all those effects. Now, the National Oceanic Administration, or the Atmosphere Administration, has done a report about the 10 signs of a warming world, in the sense that some of this we have seen before, in the sense that we have a decline in Arctic sea ice, we have an increase in the ocean heat temperature, or heat content. We see an increase in the temperature, in the air temperature over the ocean, the sea surface temperature, as well as the air temperature over land and the temperature of the lower atmosphere. So you will see that this increase in temperature is not limited to what we feel as human, but that it also relates to the atmosphere and the ocean. We see an increase in global sea levels and humidity. And of course, then we also see a decrease in the snow cover and retreating glaciers. Now, there's the question about, well, how much does the temperature, how much is it affected by human activity? So before we start into this, let us have a look at this NASA video that shows the global warming from 1880 to 2020. Now, you have seen in this video that there is an increase in the what is called the temperature anomaly over time, especially in the most recent decades. And then again, there is the human activity and the relationship between human activity and temperature. So the National Intelligence Council, and this is, by the way, a think tank that is working as well, it is working as a think tank for the intelligence community in the United States. And they have, in their most recent report, they write that climate change caused by growing human-induced concentrations of greenhouse gas emissions or greenhouse gases in the atmosphere. The National Climate Assessment states that global climate is changing rapidly compared to the pace of natural variations in climate that have occurred throughout Earth history. Global average temperature has increased by about 1.7 Fahrenheit from 1901 to 2016, and observational evidence does not support any credible natural explanations for this amount of warming. Instead, the evidence consistently points to human activities, especially emissions of greenhouse and heat-trapping gases, as the dominant cause. Now, what exactly is meant by the natural variations? So it turns out that indeed natural and human factors influence the Earth climate. So note that here on the right-hand side you have three graphs. Note that the black line here is the observed temperature, and then we have here computer simulation models that account for both natural and human influences. So if you're thinking about natural influences, those would be, for example, volcanic activity, solar activity, orbital activity. And then you have also the human influences that are, for example, land cover changes or greenhouse gas emissions. Now note that we have to take into account that every model that we are going to see, those models are trying to reproduce climate. They do not try to reproduce weather. Okay, there's a difference between weather and climate. Basically, climate is what you expect to get, and weather is what you are actually getting. Okay, I have once heard the analogy that weather and climate is very much like personality and mood, in the sense that personality is like climate, in the sense that you can have a very pleasant personality, but then your mood is in the sense that you may have a very bad day, okay, where you are very moody, if you will, okay? So here, again, you're talking about reproducing climate and not the weather. And you can see here that if you're looking at the temperature difference from the average is on the vertical axis, and on the horizontal axis you have the time or the year. Then you see that we have the temperature differences that are explained by natural factors, which is the yellow line. Then we have the temperature differences by human influences. Again, those are, for example, greenhouse gases, ozone, land cover changes, etc. And you can see that if you are combining the human and natural influences, okay, that you are getting a very exact reproduction of the temperature difference, okay, from the average. And you see that the majority here is driven by greenhouse gases, that means by human activity. Now, why is hotter air or an increase in temperature a problem? There are many problems associated with that, and we are going to look at that throughout this video. One of them is, for example, think about that hotter air stores more water. Think about that means you have a decrease, or you have if precipitation happens, the air is storing more water, and hence you are going to have a heavier rainfall. Now here again, we have the from January till December, we have record years. And note that we have the record years in terms of heat. So for example, 1926 was a record year. You have 1937, 1938. Okay. And then note that you also have a very wide gap between those between 1944 and 1980. And you see that the color shading is actually is by year. Red are the most recent years. Blue are the years that are further in the past. And you see that the new record years, that the most recent record years are all much higher than before, for obvious reasons. Now, before we start getting into the climate projections, how does climate actually look like in the future, there are three aspects which we have to cover first. There are what are called representative concentration pathways, or RCPs. Then the second concept is shared socioeconomic pathways. And then the last model is where we put them together in what are called global climate models, or GCMs. RCPs and SSPs are basically here to make climate studies comparable to each other. So the RCPs are basically scenarios that represent different greenhouse gas concentration levels in the atmosphere. And those RCPs serve as inputs to climate model. Now, the RCPs basically measure what is called radiative forcing in the year 2001 in terms of watts per square meter. Okay, that is compared to pre-industrial levels. So for example, if you're looking at the common RCPs, you have, for example, RCP 2.6. Okay, and what this means is that the radiative forcing would be 2.6 watts per square meter in 2100, that higher compared to the pre-industrial level. Note that 2.6 is so lower RCP values correspond to lower greenhouse gas emissions and vice versa. So in RCP 2.6, we assume that there is a strong mitigation efforts and a decline in CO2 emissions after 2020. RCP 4.5 means that there is a stabilization of CO2 concentrations around the year 2100. RCP 6.0 is our current emission trends. And then we have RCP 8.5, which basically means there is no mitigation efforts and there is a rapid increase in CO2 concentrations. You can think about that RCP 8.5 as the worst case scenario. Now, those RCPs are combined with what are called shared socioeconomic pathways. And you can think about shared socioeconomic pathways, or SSPs, as storylines that use quantitative measures such as population growth, income growth, and urbanization over the next decades until 2100. And how are the income levels and population in various countries, how is it evolving? Basically, you can think about those as future scenarios of socioeconomic development, and they facilitate the comparability of climate change studies, in the sense that what you are interested in research is that the results are not driven by, for example, different assumptions in terms of economic growth or population, but that those main parameters are the same, and then changes are only implemented for a given population or income growth trajectories. There are usually three pathways that are used. There is the SSP 1, 2, and 3. Note that, for example, in SSP 1, you can think about this as a sustainability scenario, in the sense that we have low mitigation and adaptation challenges. We have a relatively high growth rate in the GDP, or gross domestic product, and there's also low population growth. SSP2 is a middle of the road scenario where we have medium GDP and population growth. And SSP3 is a scenario where we have high population growth, which of course puts pressure, for example, on agricultural land, on crop production, and we also have low GDP, in the sense that when we have low GDP growth, that results, for example, that there is limited ability to actually mitigate and adapt for climate change. Now, the last big component which drives the climate change literature are what are called global climate models. Those are basically computer models to simulate the behavior of the Earth climate system, and they incorporate physical, chemical, and biological processes to represent the interaction between the various components, such as ocean, land, and the air. Now, those models, the application of those models is basically to project climate change under different GHG emission scenarios. Those GHG emission scenarios are coming from the representative concentration pathways that we have talked about. Given those climate models, we can then do impact assessment, for example, when we know that the temperature is increasing or that there is more precipitation in a particular area. We can then combine this with agricultural models to determine of how crop yields are affected. And of course, those climate models also help policymakers to make decisions about the potential consequences of climate change policy and the effectiveness of mitigation and adaptation measures. There are various components of those GCMs, in the sense that we have atmospheric, oceanic, land, and sea ice models that all simulate the various dynamics of those items. So you can think about the land surface model, that it simulates the vegetation dynamics. How are plants growing under different temperatures and precipitation? And keep in mind that, for example, if you're having a cornfield, that cornfield or forest, that forest is actually sequestering or taking carbon, CO2 out of the atmosphere, storing it in the biomass, and there's also soil sequestration. And we have to know how this uptake or this plant uptake of CO2 interacts with the emissions of CO2, for example, from fossil fuel based vehicles, for example, from the transportation sector. There are challenges associated with those GCMs, in the sense that, as you can imagine, there are very complex interactions between the various components. There is uncertainty in terms of how certain processes work. Data availability is an issue, in the sense that we have very good data, for example, for the United States, about land cover, about biomass, about soil carbon, but this may not be true everywhere. Also, those global climate models, they do have also their origin in weather forecasting, that are used in weather forecasting models, if you will. And those models are computationally extremely extensive, especially if you're doing this at the global scale. Now, let us have a look here at the emissions and temperature history as well as projections. So on the left-hand side, you see the global carbon emissions, or the fossil fuel carbon emissions. And we have the black line here are the observed emissions. And then, as I said before, those RCP scenarios are represent concentrations, represent future emissions. So here you see the RCP 8.5, for example, that is leading to a significant increase in global carbon emissions, whereas the RCP 2.6, which stabilizes emissions after 2020, we would see this decline here. Okay? How do those emissions translate into temperature increases? Now note that the CO2 that is in the atmosphere, that is a stock, in the sense that even though here those emissions, what you see on the left-hand side, those are flow variables, in the sense that you are basically just reducing additions to the stock, but the stock itself is not declining. This is why you have now this increase still in global average temperature, despite the fact that, for example, in the scenario 2.6, you do have a reduction in emissions, but since the stock is still in the atmosphere, we have this increase in temperature that is still stabilizing, but that is not reverting. Now, how those temperature increases, those global temperature increases, translate into the United States is depicted on the next slide here, where we have on the left-hand side, we have the change in temperature. This is by the mid-21st century, so around 2050. And then we have here the late 21st century, and this is just for the case of the RCP 8.5. So the thing about this as the very high emission scenario that translates into a significant increase in temperature. So let us first have a look at the temperature here, or the evolution of temperature on the left-hand side. And note that here we have the change in temperature in Fahrenheit. You can see that in the high emission scenario by 2050, we would see a significant increase in the northern part of the United States in terms of temperature. So again, we have those, despite the fact that we have global temperature increases, those translate also into regional differences in terms of temperature and precipitation, because as I mentioned before, we have those global climate models that take those various components, for example, vegetation, etc., into account. So you can see that we have in the highest scenario, so you have the mid-21st century at the top, and you have the late 21st century, so you have the 2050 and 2100 here at the bottom. And you can see that in the late 21st century, we have an increase in the average temperature of over 8 degrees Fahrenheit in the high emissions scenario. Okay, and for the scenario where we have the RCP 8.5 by 2050, we also see that we have an increase in the temperature of about 4 to 5 degrees Fahrenheit. This also translates into changes in precipitation. And of course, if you're thinking about precipitation, this is important, for example, for farming, but it also is important for the cities in the west and the southwest. If you're thinking about certain cities that have a significant increase in population and that there needs to be drinking water, sometimes also irrigation water, etc. And you see that we have this change in precipitation. Again, this would be the late 21st century in the high emission scenario, and that you see that spring and winter is going to get, in the areas of the Midwest, those are going to get wetter, in the sense that there's going to be more precipitation, whereas you are seeing a significant decrease in precipitation in in the southwest. Now, we talked about global impacts, we talked about impacts of the US, but sometimes I feel that people have difficulties to understanding what it means for them. So here I have actually put together the information from the previous models, but I have made the calculations just for Marion County in Indiana. So first of all, you have on the vertical axis, you have the minimum temperature in Celsius, in degrees Celsius, and you also have the various months, so January, February, and so on the horizontal axis. So let us first have a look at the box plots, which are the black box and whisker plots here that are depicted here. And so note that we have, what I have done is for the years 1981 to 2021, I have downloaded climate data, or weather data, and I have taken the average over this period for each month. Okay, so in a sense that I have calculated the average minimum temperature for January in 1981, for February in 1981, and so on. Okay, and so you see that the over the year from 1981 to 2021, you see that we had 1 year where the average minimum temperature was in January was close to 0 degrees, and there was 1 year where the average temperature was probably negative 13, negative 14 degrees. Okay, and so here you see then the colored line is what various global climate models, okay, those are global climate models, what the minimum average temperature is going to look like. So you can see that we are going to have, so in the summer month, okay, or spring, summer, we are going to see a little bit of an increase in temperature, but we see for the winter month that there's the expectation that temperatures are going to be warmer than what we have seen in the past. Now, what the interesting aspect is not the minimum temperature, but is the maximum temperature. Okay, so here I have done the same thing in the sense that I have calculated the monthly average temperature for each month between 1981 and 2021. And so you can see that we had, for example, here in July, we had summers that were significantly hot, but that now with the climate change, note that here I have this is the RCP 8.5, which is the most extreme example, but something that is probably reasonable to assume that this may actually happen. Then you see that we have a significant increase in the temperature in June, July, and expected temperature and August. Okay, that is outside the range of what we have observed in the past. Okay, so here you can think about this as really the heat stress kicking in those summer months. Now, the question is, how does this information about the future climate, how does this actually translate into yield changes? And actually, let me get back really quick at those changes for Marion County. Note that those temperatures here are for the year 2050. Okay, so that is mid-century. So that is basically 27 years out. So this is actually relatively close in terms of time. So now the question is, how do this information or the output from the global climate models, how do they actually translate into economic activity? And here I'm giving you an example about crop yield changes in some states, some counties in Indiana. So usually when you're modeling crop yields, you can either do statistical models. This is what we're going to use here, or you can use what are called process-based models. So process-based models is usually what is used in the biological science or agronomic science, in the sense that they really model the management aspects and how do the plants actually grow, given, for example, nitrogen, given precipitation, given the timing of precipitation, given the timing of fertilization, and so on. So here we are going to, what I'm going to present you is actually a statistical model. And there are three variables that we are looking at, and those are usually, there are many variations of how those variables are calculated. Here I'm presenting you a very simple model, and the variables that we are looking at is what is called GDD, or growing degree days, which is basically a measure of favorable growing conditions. We are looking at high degree days, which is a measure for heat stress. And then we are also looking at precipitation, which indicates water availability. So think about growing degree days basically as favorable conditions for the growth of a plant. So here, this is an example from a paper by Roberts et al. In 2017. And so think about that we have a plant, and this plant is going to grow optimally between 10 degrees Celsius and 29 degrees Celsius. And then what we are basically looking at, what those growing degree days, or this GDD, what they do is how long during the day is the plant exposed to 1 degree Celsius within the range of 10 to 29 C. So the very simplest example is, think about that over one day, that there is 1 hour of 1 degree Celsius, or that there's 11 degrees Celsius for 1 hour. Then in that 1 hour, the GDD would be 1, because the temperature has been exposed to 1 degree Celsius, the difference between 10 and 11, for 1 hour. So here in this example, imagine a day where we have 10 hours of 20 degrees Celsius, 10 hours of this is 25 degrees Celsius, and 4 hours of 35 degrees Celsius. Okay, again here this would be 25 degrees Celsius. Then the calculations you can see here at the bottom. So for this particular day, the GDD value would be 13.58. Okay, now the high degree days, which is measure of heat stress, think about this as only having a lower bound, in the sense that we say that if the plant is exposed to temperature of, say, 32 degrees and above, then we are measuring HDD, which basically means that in this condition, the plant is suffering from heat stress, which actually decreases yields. So when we are running a very simple model, where we are running a regression with 6 counties, so here those are the 6 top producing counties in terms of quantity for 2022 in Indiana. So Benton, Clinton, Jasper, Newton, Rush, and White County. Then the blue line here are the observed values of crop yields over time. So here this is clearly the drought in 2012. Okay, and then the red line is a fitted curve, where we have run a regression model with growing degree days, HDD, and also with the precipitation in the various months during the growing season. And you can see that with this statistical model, we can actually capture yield variations very good, okay, or pretty accurately. So once we have a model where we can project historic yields, then we can use the model to actually put the output from those global climate models into the yield model, into a yield model, projecting future yields that would then tell us of how this is actually going to impact agricultural production in the future. There are many more examples of economic impacts, in the sense that the impact that we have looked at so far is housing, but of course, is agriculture. But of course, there is also impact on basically every aspect of life, if you will. So here are just a few examples. Thinking about housing, where you have a strength of an increasing strength of hurricanes and more severe weather events. You see those effects already in Florida, where homeowners have difficulties to purchase homeowners insurance. Note that this is also caused by the fact that more and more expensive homes are built in Florida, and if they're built in the path of potential hurricanes, then the insurance premium is also going to increase significantly. Of course, if you are living close to the sea, then you should also be concerned about potential sea level rises. Another economic impact would be energy demand and expenditures. So before I have, for example, shown you that temperatures are going to increase in the summer and also an increase in the winter. So there are two effects, in the sense that you have an increase in the electricity consumption because you are running your air conditioning in the summer when the temperature is high. But it also means that since you do not have to heat as much in the winter due to the higher winter temperatures, that this will actually lead to a decrease in the natural gas consumption. There's also an effect on water. So think about if you have more heat and agriculture needs more water, then you have more irrigation needs, and you run into the danger of potential groundwater depletion. We see this already in the West, that you have lakes, hydro lakes that are lakes that are serving a hydropower station, that there's not sufficient waters, or there's lower river water flows. And since you are producing electricity from those hydro stations, that you can also expect a change in the electricity production subsequently. There's also, of course, a declining productivity at high temperatures. So this would impact the labor productivity. This assumes that you do not have, for example, air conditioning at your workplace. Now, this may not be an issue, for example, in the United States, but it may actually be an issue at the global level. Most importantly, there are also going to be health effects from the severe heat and the potential air pollution. So think about, for example, that if you have a higher temperature in certain areas, or if the temperature is increasing, for example, in Indiana, that also means that disease-carrying organisms, such as mosquitoes, they can expand their area where they are active. If they're carrying disease, that would also then translate directly into increased health issues, increased mortality, increased healthcare expenditures. You also have, especially if you're thinking about more fossil fuels being burned, you're going to have issues related to air pollution, the particulate matter, and ozone. Longer growing seasons are also going to result in more pollen, more allergens, which may also cause health issues. And of course, there are many more health issues associated. Now, keep in mind the importance of climate change, or the importance of climate change policy relates to the fact that there are significant economic damages associated with climate change. So we have here a table that is just showing some aspects of economic damages in 2019 related to climate change. So on the column here, this is again the most extreme climate change scenario. When we have annual damages, note that those are not cumulative damages, but those are annual damages. That we have the labor sector, the reduced productivity. For example, you have $155 billion in annual damages. You have also damages in terms of extreme temperature mortality, coastal property. I mentioned that before about, for example, sea level rises, hurricanes, etc. So here you have a list of damages by economic sector. And then if you're thinking about the climate change policy, for example, if you want to be on the path of RCP 4.5 and not RCP 8.5, then you can look at the what are the savings in terms of annual damages, and then you have to compare that to the cost associated with, for example, moving from the RCP 8.5 to RCP 4.5. Here you have the summary of the some economic impact studies. Again, here you have the annual damages from labor and how it actually, if you're moving from RCP 8.5 to RCP 4.5, the projected annual savings due to global mitigation. Okay, and again, this is data consistent with the previous slide. You see, for example, that the majority here is that there's a change in the hours worked due to extreme heat, that especially in southern Texas or also in Florida, that we see a decrease of 5% or more in terms of hours worked. There's not only an impact in terms of economic damage, but there's also an impact on national security. And again, this is data, or this is the data from the National Intelligence Council from their Global Trend Reports 2040, where they think about, again, they have climate change with higher temperatures, extreme weather, and sea level rise, paired with environmental degradation in terms of land, water, and air pollution, and that those factors are actually eroding human security, what they call human security, in the sense of food, water, energy security, and human health. This leads to more migration and loss of natural capital, and that ultimately then leads to instability and conflict. So there are not only economic costs associated in terms with climate change, but there are also national security impacts of climate change. Note that the National Intelligence Council is producing those global trend reports every couple of years. So, and I have read the 3 previous ones, and climate change is always one of the main issues that the National Intelligence Council is concerned about. And why they are concerned about, you can see this on this slide. In the second part, we are going to talk about climate change policies. We have seen before that we have greenhouse gas emissions that are increasing global temperature, and that this has a lot of consequences in terms of economic damages, health effects, etc. Now, the question is, how can we reduce the greenhouse gas emissions? And economists have a very simple view on climate policy. The fundamental problem associated with carbon emissions or with greenhouse gas emissions is that individual actors, that could be the consumer, that could be firms, they do not incorporate the cost associated with carbon emissions. In the sense that if I'm driving my car, I emit carbon dioxide, and that cost, the damage that is caused globally, I do not account for this damage. The economic solution is that we should simply price carbon emissions, and what this does is it gives individual actors, that could be firms as well as consumers, an incentive to reduce activities that emit carbon. because it changes a carbon price, changes the relative price between products and, and increases the price of carbon emitting items. So for example, if you are consuming natural gas, and then if you have a carbon price, then the natural gas would become more expensive compared to other products, and you would be reducing your consumption of natural gas. Note that a carbon price would not apply to products that do not emit greenhouse gas emissions. Now, human behavior is that humans are driven by incentives presented to them, and there may be adverse or unintended consequences associated with those policies. And so sometimes it is important to not lose sight of the big picture in an interconnected world. So for example, the United States is very efficient in terms of beef production as it relates to carbon emissions. So previous research has shown that if you are actually, for example, if you are imposing a carbon tax on US cattle producers, what that would do is it would shift production in other countries where there is much higher emissions associated with beef production. Okay, so you could actually end up in a situation where you are shifting greenhouse gas emissions to other countries. Okay, this is an effect which is called leakage. Now, economists have a very simple view in the sense that we simply tax carbon emissions or carbon-intensive products, but it turns out that this is actually problematic. So here on this graph, or in this table, you have what is called the Consumer Expenditure Survey 2020. And note that those are, this is compiled by the US Census Bureau every year. And they are conducting a survey asking consumers where they spend their money on. So here in the first column, you have the income decile. Okay, so here you have about 130 million households. Note households and not people. So think about that the average income of the lowest 10% of households in terms of income is about $7,100. Then, and the top 10% of households, they have an income of about $290,000. Now, what is interesting about this graph or this table are two things. First, note that even basically the bottom 50% of households in the United States, that through transfer payments, their income after taxes is actually equal or higher than the income before taxes. Okay, that means that a lot of households actually benefit from transfer payments from the government. But when it comes to carbon emissions, then have a look at the last column about the energy share. So it turns out that low-income households, they spend, since energy is one of the fundamental goods, low-income households spend a much higher share on energy-intensive products than high-income households. So here the energy share is everything related to natural gas, electricity, and also gasoline. So the lowest tier, or the lowest decile of households, they spend 8% of their income on energy-related items. What this means is that if you are imposing a carbon tax, then the lower income households are hit much harder by the carbon tax than the high income households. Which also means that if you want to impose a carbon tax, that this should probably go hand in hand with transfer payments, such as that low-income households are actually compensated for their higher tax share in terms of carbon-intensive goods. Now note that the carbon tax, so sometimes people wonder, why do we impose a carbon tax on items, but then transfer money back to households in terms of lump sum payments? And it turns out that the carbon tax actually works independent of how you, what is called, recycle the revenue. So even if you give the lump sum tax payment, if you give a lump sum tax back to the households, they're still changing their behavior in terms of how much they spend on energy intensive goods. Because as you have seen on the last slide, if you are having a carbon tax, then the carbon intensive products get more expensive relative to low carbon or no carbon emitting products, and that actually changes behavior. Now you have, in the US, you have a lot of efforts in terms of reducing carbon emissions. And one aspect is the road transportation sector. So here you have increasing fuel efficiency, and you also have the push for alternative fuel vehicles. So those are, for example, electric vehicles or plug-in hybrid vehicles. There are also numerous policies in the European Union that aim to increase alternative fuel vehicles. Now, for those policies or for those policies to work, what you need is you have to make sure that if you're pushing electric vehicles or if you are subsidizing, for example, electric vehicles, then although those vehicles have zero tailpipe emissions, the electricity to power those vehicles still comes from power plants. So if you are replacing, say, a fleet from gasoline vehicles to electric vehicles, then if the electricity is produced by coal-fired power plants, then the reduction in emissions is actually going to be very small compared to the gasoline vehicle. But even though when you have the policies that are aiming to increase the share of electric vehicles, there are various aspects and consequences beyond the road transportation sector. So for example, in the United States, road and infrastructure funding is actually financed by fuel taxes. So if you're subsidizing electric vehicles and you have more electric vehicles on the road that do not pay fuel taxes, then you have less funding available for road and infrastructure projects, because you have a decrease in the fuel tax revenue. Increasing the fleet of electric vehicles also has implications on electricity production and transmission expansion due to different what are called load profiles. So for example, if you have in the Southwest, if you are increasing the number of solar panels to produce electricity, now those solar panels do not produce electricity at night for obvious reasons. But then when most people are charging their electric vehicles, that would be, for example, when they are at home and at night. So there you would have a mismatch between the demand of electricity that would be during the night for charging your electric vehicle. But if you are relying on solar energy, that would happen only during the day. Okay, so there you have to make sure that there is an alignment of supply and demand. Another road policy that has been subject of my research are US biofuels. So MTBE was an additive for gasoline to raise octane. However, it was banned due to health concerns, and maize ethanol or corn ethanol served as a substitute for MTBE. Now, there were also other concerns around at the beginning of the 2000s in terms of energy independence and greenhouse gas emissions, and hence there was a push to actually increase corn ethanol as a blend with gasoline. Note that this led to a significant increase in maize demand, but this was not without controversy. Okay, because if right now about 1/3 of US maize production or corn production is actually used for ethanol. At the same time, in around 2008, you also had the situation where we had high oil prices, and since you are able to blend ethanol with gasoline, you basically were able to substitute the high oil price or the high gasoline price. You were able to mix that with ethanol, which was much cheaper, and hence that spurred also the demand for corn ethanol in the United States. Now, there is, of course, concern about how the decarbonization or this climate change policy to subsidize or to push for more electric vehicles, what the consequences are for agriculture. As mentioned before, about 1/3 of US maize production is used, or US corn production is used for ethanol, and about 1/3 of global production, of global corn production, is actually coming from the US. So there's the question about the long-term decline of corn ethanol demand and what the welfare implications for farmers and consumers are. Some say that there is the possibility to actually increase the use of ethanol in sustainable, what are called sustainable aviation fuels. But again, the industry or the market for sustainable aviation fuels is actually in its infancy. Okay, so there it is not clear where this is going to go in the long run. Now, in conclusion, we can say that climate change is a very complex topic. There are many aspects that are related to climate change, and it is very difficult to actually capture them all in just a very short video. We have seen that, for example, there are going to be impacts of climate change on crop yields, and that is going to have food security implications. But if you're thinking about in the US, if you're thinking about farmers in the US, you will see that there are new opportunities for landowners to actually mitigate carbon emissions. There is what is called carbon farming, for example, and basically what it is that farmers were to switch from, say, intensive tillage to no tillage, and they could actually increase their carbon sequestration in the soil. There's also the possibility to construct what are called anaerobic digesters. So anaerobic digesters, think about them as large tanks where you are feeding in biomass, for example, animal manure, and then the animal manure is decomposed anaerobically, and that releases methane. That methane can actually be used to generate electricity or generate renewable natural gas. So in conclusion, climate change is a very big concern, and there's going to be a lot of action necessary to avoid major damage. But again, here we need collective action, because if you have individually self-interested actions without any constraints, that leads to externalities, that leads to carbon emissions. There are also a lot of unintended consequences that are possible, and hence we need integrated approaches. In order to make climate change policy effective and also efficient, we also need to take into account the distributional effects because they are important for societal and political reasons.